I'm really delighted to welcome you to this Research on Tap. So the topic for today is accelerating the energy transformation pathways to decarbonization and sustainability. And I'm really delighted that this particular one is being hosted by Peter Fox-Penner, the head of our Institute for Sustainable Energy.
An institute like ours that's a community of scholars and policymakers and students who are interacting with each other to have an impact, a near-term impact on the world. Now, of course, our main mission is to do research that advances the cause of sustainable energy. And I think rather than say anything more about it, the very best thing I can do is let the speakers speak for the research that all of you are doing with us.
I'm Robert Kleinberg, Institute of Sustainable Energy. As you see on the slide, my topic is methane emissions detection, technology versus regulation. It would be much nicer if it was and regulation, but unfortunately it's not. Those two things seem to be in conflict these days. Methane is, as many of you know, the second most important greenhouse gas that's going into our atmosphere to affect climate. About 15% of total global methane emissions come from the oil and gas industry. And so because I'm come from the oil and gas industry, I'm kind of the unsustainable project in the Institute of Sustainable Energy. So that's what you're going to be seeing. So methane's an important gas, but it's also elusive. It's hard to estimate how much is coming out of our infrastructure. So in 2016, the Environmental Protection Agency mandated an inspection regime with two approved methods. In the upper left is me implementing one of those methods called Method 21. And here I am at a well site infrastructure, checking every flange, every valve, every connector, every pump, looking for leaks. And let me tell you, this is frustrating and time-consuming and inefficient and pretty ineffective. Now, there's another way to do it, and that's illustrated in the upper right, where you put a infrared methane sensor in a Cessna, fly at 1,000 meters altitude, and fly over an oil field. And there you find the biggest leaks very quickly and very efficiently. And what you find is that only about 2.5% of the total well sites, for example, in the Permian Basin, are responsible for more than half the total emissions in that area. And it's really incredibly effective and efficient, and you find the biggest problems first so you can solve them first. And as our technology improves, that percentage will go up. However, as the slide says, no path to approval. You could fly this all you want voluntarily, but you still need to go back on the ground with good old Method 21 and check every flange, and it's really dumb. So one thing that's happening in the House of Representatives now is that there's an act in Congress, several of them actually, which are going to roll back all the Trump-era depredations of this original methane rule. And so what the people who are writing these laws are saying, well, let's just roll back to 2016 Obama-era rules. There we go. And get rid of all this Trump stuff that makes things worse. So I go in there and I say, no, don't do that, because you're going to be stuck with this old-fashioned crummy technology. Let's make sure we're using the most innovative stuff. So just looking at the last two lines on the table, I'm not going to go through the whole thing. So in the old rule, to introduce a new technology, the sensitivity had to be better. No, that's not what you want. What you really want is greenhouse gas reduction. Keep your eye on the ball. And finally, you want to be able to write regulations that encourage innovation, not discourage it. And that's what our amendment does. So our amendment is now, I'm glad to say this, now working its way through Congress. We're hoping for the best. No promises yet, but that's the update. Thanks very much.
All right, my name is Justin Ren. I'm the associate professor at the Questrom across the street, and I'm also affiliated with ISE. This is a quick summary of a book that Peter and David Germain we put out early this year, and the name is Melting the Ice, and I'll show you what the ice mean. basically, it's about EV, but particularly it's about how to promote and accelerate the adoption of electric vehicles. And here we're focusing on charging infrastructure. Now, why do we want to promote EV other than we are running out of gas? Of course, somewhat like related to Rob earlier said, transportation has a, well, here it's about 30% of the CO2 emission. And by the way, I learned that the main thing is deadlier in terms of tracking heat from, yeah. So it is very important with transition from the internal combustion engine to electric vehicle. And the trajectory is good. If you look at the graph on the right, countries are adopting rather quickly, but the base is small, I have to remind you, so that we need to do a lot more. Now, this book is from a series of case studies we did about cities around the world. And actually, I probably can show you what cities are involved. Now, we did LA, and we did Beijing, we did Oslo, you probably can see right here. But we also did small towns like Brookline right here. The idea is to learn from those localities what we can gather and share in terms of promoting EV charging infrastructure. So this graph essentially captures what we think are the key factors, and I'll tell you a few kind of stories or anecdotes. For example, we think both monetary and non-monetary incentives are important, right? Of course, cities like Oslo dole out, or US too, dole out a lot of money for for them to buy. But you can also see a lot of clever incentives. For example, LA, some of you already know that they use high occupancy, HOV lane as a kind of, carrot. So if you have that green sticker, you can get into a faster lane, although recent news said it's so congested, the HOV lane is not getting any faster as well. But also, if you look at cities like Beijing and Shanghai, it's kind of heavy-handed. If you want to get a gasoline car, getting to a line, either lottery or just waiting line. Whereas if you want to get an EV, you can get it. You can get license and registration today, right? So, but also we look at say workplace charging, and some of you already felt the pain about BU. We don't have enough EV chargers, but if you look at San Jose in California, it has the highest percentage of workplace chargers. And of course, home charging and public charging are both important factors. So, and I guess it's really just a appetizer. If you, I'm going to flip back to this slides. This book is freely available on our ISE website. And if you feel like donating some money to us at ISE, you go to Amazon and buy that too. All right, thank you very much.
Thank you for the invitation. I'm very happy to be here and have a chance to talk to you. I'm Michael Karamanis. I teach in the College of Engineering, so one of the few sort of card-carrying engineering speakers here. And my area is systems engineering optimization, which is the cyber part of the cyber physical system that energy systems are like today and are progressing to be in the future. So everybody talks about renewables, everybody talks about electrification, changes on the way that we consume electricity, but I do not think that we speak enough about how those two interact and how this cyber physical system, the cyber in the sense of information, coordination, control, and so on, and physical in terms of wires, of batteries, of generators, renewable generators, and so on, can coordinate. So here is first a very quick view on how these things interact. So you have the wires, you have the transmission and distribution system. Transmission system is the high voltage lines that you see out there, where when you when you drive in the open, in the countryside, and large generators and large consumers are connected to that. Conventional generators are coal plants, natural gas plants, but also more prevalently wind farms and other renewables. Now, one of the ways that these interact is through losses and through congestion. So it's possible that a line in this huge transmission network is congested and you can't absorb more cheap renewable generation, because electricity has the nasty habit of following the laws of physics, and then going from A to B, travels over all possible paths in proportion in inverse proportion to losses across those paths. So if there is a line in any one of those multiple paths that you can use to go from A to B that's overloaded, then if you try to extract more cheap electricity at A and feed load at B, some of that will go over the line that's congested, and bang, you can't do it anymore. So then the issue is how to deal with that by changing dynamically the interconnection, the architecture of the transmission network at the distribution level, which is becoming more and more important, because this is where the cars are going to be, the electric cars are going to be. This is where a lot of renewable generation is going to be. We have a lot of interaction in terms of the transformers and the assets of the distribution network degrading or not being up to par if the transmission, if the renewables and let's say the electric cars do not coordinate. So being able to match this, being able to have cars charge not at the same time so that they blow up transformers, be able to have to get photovoltaics to assist with the control of the voltage and the quality of power is very important. So how do we do that? The suggestion to do that is by trying to calculate, to understand the marginal cost of consuming and generating electricity at various points of the network that represents the actual marginal costs of the transmission, the distribution system, and these new loads. So being able to do that is very important, and systems theory allows us to do that. Computer science allows us to do that. Electronic platforms allows us to do that. So we have to study and see whether this is possible, and also, of course, investigate the impacts, the socio-economic impacts of going forward in this sort of coordination. Thank you.
My name is Emily Ryan. I'm assistant professor of mechanical engineering, also part of the division of materials science and engineering. So my work is fundamentally based in kind of computational modeling of various energy systems. And so we work in a lot of different areas, from carbon capture and fuel injectors and nuclear systems, and also in batteries. So today I just want to tell you a little bit about what we're doing with some of these high energy density batteries. So just to give you a little background of what's going on, I think some of the previous speakers really line it up nicely, is that EVs are skyrocketing, right? There's a lot more EVs hitting the streets, and they're developing a lot more models. The problem when you look at that is the batteries that you're using. Lithium-ion batteries are kind of the gold standard used today, and although they're great, and they've really allowed a lot of advances in portable electronics, EV, and everything else, they're not going to work if we're looking at long-term advancement of electric vehicles. And then to what Michael was just talking about, when we were talking about the grid and getting adaptive grids, this idea of grid storage. So what people are starting to look at are new technologies. And so you can see on the left-hand side here, I show some of these different technologies. What we're really looking at is higher energy density batteries. When you have a higher energy density battery, that means you can get more power out in a smaller volume or a lower weight. So therefore, we could get cars that go farther or that have smaller batteries in them. But to really get there, we need new technologies. If you can look about midway up there, you can see lithium ion. We've made great advances in them, but we're really starting to approach kind of the theoretical limits of where we can go with lithium ion. And that's just really due to the chemistry. And so if we really want to go surpassing that, then we have to look at new battery technologies. And a big area of that is things like metal air batteries. Metal air batteries like lithium, lithium oxygen, or lithium sulfur have a lot more potential theoretically to get really close to gasoline in terms of their energy densities, which would make them a lot more valuable. The problem being is they have a lot of fundamental technical challenges to overcome before they can actually be commercialized. And so that's where the research really comes in. And the areas that this goes to are a number of things, but one of the biggest things is long-term performance. If we want them to last for lots of cycles, we need them to have a high performance. They don't right now. A lot of that comes from material issues, stability of different materials working together. And then one of the biggest ones is a safety issue. If we're going to put these in the cars, on the streets, we have to make sure we have safe systems. So to that end, I said we do computational modeling. We've been looking at one issue of many that are going on in these battery systems, and we use computational modeling to try and look at interfacial stability in these batteries. And in particular, where you look at the electrode-electrolyte interface, especially in a metal battery system, as you charge or discharge it, operate it, and then charge it back, you've got lithium stripping and plating off the system. When it does that, it doesn't do it uniformly. Instead, what you get are what are known as these dendritic growths, which are kind of these tree-like structures you can see in all of our simulations here. And what happens over time is that this leads to drops in performance. You get capacity fade, so you don't have your cell phone or your laptop lasting as long. That's what we see every day now. You can have safety issues. If you've ever seen something like a fire, a laptop fire, that's what it would be. And you just limit the cycle life. So what we do is we have modeling that we're trying to understand fundamentally what's going on with this dendritic growth. And we do this to look at a lot of different areas of this. But one thing we look at kind of on the bottom right-hand side is the idea of separators. There are separators in batteries, which are porous material. How could we design that might be able to affect local transport and affect the dendritic growth? So could we inherently limit that growth using something like a separator that's already there? We also look at new materials. So something like an ionic liquid crystal has properties which would allow it to inherently have control over mass transport. So could we use new materials in the system? And then the newer area we're looking into is the idea of how we operate it. So charging conditions. So we charge our batteries right now, and depending on how fast or slow you charge it, that'll affect dendritic growth. Can we come up with new protocols for charging that would allow something like fast charging, but not affect the performance? And so we're looking at all these different aspects through various different models and working with different companies and government funding to try and understand this better.
Michael Gevelber, also in the College of Engineering, Mechanical Engineering Department, and member of the BU Climate Action Planning Group. So I'm very interested in getting ideas and technology from what we do here at the university into practice, because we need a lot of help in that. What's my focus? It's commercial buildings, rather prosaic. Why is that important? It uses a fair amount of the energy, but it accounts for 37% of electricity use. So huge opportunity to reduce our greenhouse gas impact. Huge amount of waste, over 60%. And why is this important? I focus on HVAC systems. It accounts for 40 to 60% of building energy. And what drives this energy use? It's the amount of airflow. So if you squint up at these little things, slots there's $16,000 flowing into this room, but nobody's aware of it. And so what our engineering research has done is, brought a focus on that, and we're developing technology to improve it. What enables us to do this research? It's the university, all these wonderful buildings. We've got over 14 million square feet, over 300 buildings, many different types, from residential to laboratory, and great opportunity to do this research. There we go, 16,000. So want to tell you about two particular projects. One is the HVAC control architecture. And what we want to do is, there's a trade-off between how much outside air you use and the indoor air quality. And the more outside air you use, the more expensive it is. And we do this under different regulatory environment. There's an ASHRAE standard. California has its own standard. And the Berkeley Labs plus Harvard proposed even more outside air. So what I'm plotting here on the vertical axis is the cost, and on the x-axis we're plotting CO2 levels, which is indicative of the indoor air quality. And the orange line is what our conventional practice is, and through our research, we're able to improve air quality, but at lower cost. So again, an area we want to get this research out to, but really important to be able to address the question of what air standard do we really need? And there's an opportunity to collaborate with the School of Public Health. More recently, we kicked off a study on how do you measure air leakage in building? Why do we care about this, especially in residential buildings? Because air that leaks out to the exterior, that's increasing your energy use. But air that leaks between apartments, that's decreasing your indoor air quality. And so we're developing a method that can distinguish between those two. Again, another great opportunity because School of Public Health does studies out in the field. We now have a much better tool to be able to use with them. Thanks.
So over the last couple of years, I had the privilege of leading a group of faculty and students here at BU and a team of consultants to assess the technical options available to the city of Boston to enable it to reach its goal of being carbon neutral by 2050. And we focused on a wide range of, or every aspect of city life, but I'm going to talk about one in particular today, and that is buildings and how to decarbonize the city's buildings, and in particular dive into a social equity aspect of actually doing that. So here are the results for the building sector. The vertical axis is greenhouse gas emissions from the city's buildings out to 2050. Relative to a baseline, the top line there, deep cuts in emissions come with that first orange drop there, with city action that requires all new construction to be net zero, and action that drives the adoption of deep energy efficiency measures such as whole building retrofits. The second strategy is thermal electrification, which refers to the replacement of boilers and furnaces burning natural gas with heat pumps, with heat pumps and boilers that run on electricity. The drop in emissions represented by the dark blue arrow there is caused by electrification of thermal services with a regional grid that is 80% free of GHGs by 2050 as required by state law. And then the final drop there, the gray, is the city could go out and procure renewable energy like BU is doing, or the wind energy, and get to an effectively 100% clean supply of electricity. There are still some residual emissions with buildings that are very hard to electrify. So we assessed a lot of the technical issues and economic issues associated with this. But I want to focus, as I mentioned, on equity issues. How do you decarbonize these buildings in a socially equitable manner? Boston is a majority-minority city in which 1 in 5 people live below the federal poverty level, and where the cost of living is in the stratosphere. Very low-income households pay 25% of their monthly income for fuel and electricity, and every winter many households face eat or heat decisions. Type of ownership also is important. Shown here is a map of the city's neighborhoods, and we showed about 22,000 out of 260,000 households in the city. Shown in orange are 16,000 buildings in what are called hard to retrofit buildings. These are buildings that are renter occupied, they're multifamily, and they are households with incomes below the city's median income. Those are hard to retrofit for a variety of reasons. Shown in green are 6,500 single-family homes that have a median income above the city median and are owner-occupied. These are easier to retrofit. Neighborhoods with the highest concentration of harder to retrofit homes, Dorchester, Roxbury, Mattapan, East Boston, parts of Hyde Park, Mission Hill, coincide very closely with the neighborhoods with the highest concentrations of socially vulnerable populations. The pattern is simple. Many socially vulnerable families live in buildings that are hard to retrofit, the ones who need it the most are the hardest to reach. We describe in our report the benefits that accrue to energy efficiency, and there are a lot of them, and they accrue disproportionately, if properly designed, to socially vulnerable populations. Energy cost savings generated by efficiency preserves housing affordability and reduces energy security. Energy efficient buildings are healthy buildings because they reduce indoor air pollutants and other contaminants. And energy efficiency is a relatively labor intensive industry, so there's a real opportunity for workforce development. So in our report, and you can get copies of the reports at the ISE website, we have a technical report summary and a social equity report. We describe how this is a real opportunity for the city through intentional design, which it requires, to incorporate equity from the start in its path to becoming a carbon neutral city. Thanks.
Here, I'm going to emphasize aspects of the home environment and built environment that connect to health, particularly focusing on housing. Clearly, as we try to decarbonize, and buildings are such an important aspect of that, we need to remember people live in homes, people work in buildings, and we need to keep the health and well-being of those populations in mind. And I think Cutler alluded to this point that the attributes of homes are not equitably distributed. The top figures from a paper we wrote a few years back looking at data from the American Housing Survey, which gave things that are frankly quite intuitive. Lower income households have smaller homes, older homes, and tend to live closer to traffic and industry sources, and tend to have attributes like being uncomfortably cold for a period of time or having cracks in the walls that can contribute to obviously energy inefficiencies as well as exposures to environmental contaminants. So you have the nexus of a number of different factors, and what that also means is that there are opportunity spaces there to increase energy efficiency and also to improve health. What the figure on the bottom left shows, this is from a continuation grant that we recently submitted for our Environmental Health Disparities Center that focuses on housing, and this really reinforces a point that Cutler was making, that energy insecure homes, those who are battling with this heat or eat phenomenon, have a number of health consequences that can lead to increased indoor air pollution. You may use your gas stove to provide supplemental heating, and that creates obviously exposure and health challenges. Inadequate exposures or exposures to extreme temperatures rather have health consequences, and the socioeconomic ramifications of having energy insecurity directly affect health. So in our studies, we're trying to look at the various pathways by which energy or housing insecurity can connect to children's health. Another thing just to show from a modeling paper we recently put out, which is the panel on the bottom right, is that this has enormous consequences. So we modeled for different retrofits in low-income multifamily housing, what does it do for energy costs? What does it do for population health costs through reductions in ambient air pollution? And what does it do for indoor air quality related health? And you can see the indoor air quality health is on a different scale than the other two. And so if you do a retrofit that adversely affects indoor air quality, it will wipe out all of the economic and population health benefits. The flip side is if you do it right and you retrofit in a way that improves indoor air quality, you get a triple dividend: better economics, better population health, and better occupant health, but you've got to do it right. Another aspect of work that we've done transitions from the homes to the built environment, and another aspect of thinking about decarbonization and sustainable energy is planting of trees, maintenance of green space. And so we've looked at urban heat islands in the upper left-hand corner, as many others have, and we all know that exposures to extreme heat are inequitably distributed given both heat islands and the attributes of homes. The question is, what are the health consequences? Quickly running through the three panels, on the top right we showed SIDS, or sudden infant death syndrome, associated with increases in temperature, where this is largely seen among black versus white populations, attributed in part to aspects of the built environment. We've also shown that places with more green space have, on the bottom left panel, reduced effects of air pollution on mortality. It's sort of a complicated plot, but P75, that's places with more green space, and you can see the effects of air pollution are reduced in those settings. Finally, on the bottom right, this is a plot showing birth weight and its correlation with green space, and as areas have increased amounts of green space available, you actually see increases in birth weight, and that has public health benefits across the entire life course. Thanks.
So I wanted to share some of what we're working on in the context of nature-based solutions, which is a phrase that's received a lot of attention recently, and I think we need to consider very critically, are nature-based solutions good, and are they the right solution for the right problem in the right place? So what most of my lab has worked on, and I've spoken at other Research on Tap's events, is the carbon in decarbonization. So I'm going to just highlight it, and you could ask me about it during the on tap portion. We do a lot of work modeling emissions. This is from the New York Times last month that covered some of our work on developing greenhouse gas carbon emissions inventories. We also measure how those emissions end up in the air. And these are measurements, the black points are on the roof of CAS. And so these are measurements in Boston looking at CO2 and methane and how that carbon ends up in the air. So you could ask me about that later. That is 90% of what my lab does. What I'm really excited about at the moment, though, is some of this green space. So this is Boston. You can see Comm Ave, you can see the public garden, you could see all that green stuff. And we've been working on developing some new sensor technology to measure how water moves through plants and what that water movement through plants does to climate. So this is a little data logger, and we've inserted it into the tree, and we're measuring the water movement through the tree. So water is coming from the soil through the tree, ending up in the atmosphere. When the water changes phase from liquid to gas, it cools. And it cools substantially. So this is Arlington, town where I live, and the panel all the way on the left is a land cover map. So it's a simplified classification of what kind of vegetation you have in different parts of the city. So if you have leafy green residential areas versus areas that have spindly street trees, those areas translate into a very different climate that's experienced there. The middle panel is showing land surface temperature. This is the satellite-derived estimate of surface temperature. And you see a large spatial coherence between the amount of vegetation you have and how hot it is. And that is directly proportional to the amount of canopy cover and the surface temperature. And so we've been taking some of those measurements of water movement through trees, this sort of satellite imagery, and analysis of how hot it is where and how the vegetation relates to that, and thinking about the future in that decarbonization context and in the nature-based solution context. So this figure's a little bit complicated, but it's really cool. So shown on the y-axis is a term referred to as the Bowen ratio. It's the ratio of the sensible to the latent heat. So how much of the incoming radiation that we have coming in from the sun is being converted into heat, increased temperatures, versus being used to evaporate water. And that's that water movement through trees. If you have more sensible heat, it's going to be hotter for the same amount of radiation input. If you have more latent heat, it's going to be cooler. And so on the x-axis are model runs that we did using the weather research forecast model. And my colleague Dan Lee ran these, and we looked at how the amount of canopy extent that you had in Boston at 10% canopy cover, 25% canopy cover, or 50% canopy cover related to what the resultant temperature was. And that's what's in red below. So these are summer estimates during a heat wave, I'll point out. So from 34 degrees C to about 32 degrees. I'm out of time. I'm going to be fast. Trees cool. But trees cool much more than we thought they did. In these models, we assume that plants run out of water. In cities like Boston, they don't actually run out of water. And so if we release the constraints of water limitation, which we do through management, trees do a lot more than we thought they do.
Great.
So I'm here to tell you a little bit about the water research that we have been doing in the Institute. We started out 3 years ago with a project in Texas. In the last 6 months, we have launched a project in the Merrimack Valley. This is in collaboration with Joseph Benzaoui, who's one of our research fellows, and Michael Grinspan, who's writing his thesis in the Kilachand Honors College just before graduating in the summer. We also were led into digging in on the Merrimack by Paulina Schwartz, who's one of our fabulous research fellows, and that's also brought us into collaboration with Wendy Heiger-Bernays and Beth Haley over at the School of Public Health. So it's a really interesting set of questions that emerge. In Texas, of course, questions are often more about supply and demand, and do we have enough, and what about when there's a drought? In the Merrimack Valley, you've got many more questions about quality, what's happening when there's a combined sewer overflow, how are people impacted by the water quality. What I wanted to do in these 4 minutes is just step back and share with you the framework that we found is kind of useful in an overarching way in thinking about these questions. So what's the fundamental challenge here? We all tend to take water for granted, especially in Massachusetts. Nonetheless, when you start looking, even here in Massachusetts, the Merrimack Valley is not that far away, you pretty quickly start to realize that if you take a closer look, the sustainability, resilience, and affordability of our water is far from guaranteed. It's not even consistent today, even in places fairly close to home. So some of the trends underlying that are you've got many urban populations that are growing rapidly. Our water infrastructure across the US, as well as in other parts of the world, is aging notably, introducing a number of quality concerns and supply concerns. And then you've got climate change, which is making natural supplies more variable. It's increasing stormwater surge, and that's creating another set of challenges. Noting on the right-hand side that you are seeing projections of water prices increasing by 41% in the next 5 years. Michael Grinspan was just showing me that if you look at what the average household spends on electricity versus on water, you're seeing a crossover point just in 2024, where we're going to be starting to spend more on water than on electricity. So kind of interesting that in the context of energy, there are many programs to support affordability, relatively few on the water side, and that is something that's going to need to change. While I haven't been explicit here, closely associated with affordability is a whole set of equity issues. I would imagine it's not a surprise to many people in this room that unfortunately the community is most likely to be experiencing challenges with water quality are those with high environmental justice percentages in their populations. And so that's another part of the challenge. So we've got various tools that we've identified to address this relating to planning, financing, infrastructure, and metrics. What we found in our 3 years of work in Texas is that we've dipped into all these different pieces in different parts of our project with the same partner utility. So it's really helpful to be considering all the different approaches. I just want to wrap up with this diagram, which is intended to convey kind of a different paradigm. In conventional water management, we think about drawing from a supply, using our water, treating the sewage, and discharging it. We think about stormwater separately. We think about pushing it away from our cities and homes as rapidly as possible. There's a new approach, integrated water management, also referred to as One Water, brought in from Australia, which recognizes the connectivity between all these types of water, raises questions like, why are we treating water that we use to water our golf courses to a potable standard? How can we use green infrastructure? All those kinds of questions. So I look forward to talking to you more in the On Tap section of today. Thank you.
Hello, everyone. I'm David Germain. I'm Associate Director at the Institute, and I'm going to talk to you today about transitions that are just and how we're going about doing that in our research. About 18 months ago, we started we signed an MOU with the United Nations Economic Council in Europe, the UNECE, working with the Sustainable Energy Division, where we thought originally we were going to do some scenario work on pathways, but we ended up helping the Sustainable Energy Division try and figure out how to convert concepts of transforming infrastructure. Most of the infrastructure in Europe is fine except for the Eastern European parts of Europe, and they really need a lot of investment and support in order to transform their energy infrastructure. Their energy infrastructure is mostly coal, and so we found ourselves in a place where we were starting to help them figure out how you go about doing a real transition in coal. Well, under the United Nations sustainability goals, the focus is on really a just transition and trying to address as many of those goals as possible. Which leads me to the first slide. This is a picture of what we put together in terms of working with the UN to help them figure out all of the different elements that go into creating a just transition and driving and accelerating the migration out of coal and into other energy resources. Very briefly, you have to integrate technology and innovation to drive transformation in the use of energy assets. There are legal, regulatory, and policy issues that are huge, that have huge implications. Finance, investment, and value creation are critical, and economic development and community development are really critical as well. And all of those have to be orchestrated in a way where they work together and they begin to inform each other. And as they inform each other, all of these sort of outer rings of different aspects of the regional or local area in which you're trying to deal with, say, a coal plant and its closure, all of these things really need to be addressed to achieve a just transition. But in addition to that, you're not really going to get very far in Eastern Europe if you don't address those kinds of things. So that was kind of what we did. To our surprise, the Sustainable Energy Division said, well, we've had these concepts, but we haven't really been able to figure out how to actually make them work. So they started shopping this, and I can't believe it, but they really liked it. So we ended up spending a whole morning at the Sustainable Energy Conference in Geneva that was running in parallel with the UN Climate Week, where we spent almost a whole of the morning going through this and talking about how we make this happen. We had representatives from Germany and other places who are trying to do aspects of this. So that's where we are, and we're trying to head forward and try and do a pilot project now in Poland with trying to make this happen. To make this happen, this is kind of a Rorschach experience for you. This is kind of the scope of what you have to think through and manage in order to execute a just transition around coal. This is a generic supply chain for what a typical coal power plant might have it in its sort of radius. In Eastern Europe, in particular, local communities are very much integrated into power plants because the power plants are built with the communities around them. So the usual argument is, well, we can't close this plant because we'll destroy the community. So in order to deal with the community problem, you really have to look at the supply chain, because every node along the supply chain here are people. It's not just that there are events and contracts that have to be done. There are people that have to be moved forward into the future. And I could talk about this forever, but I've run out of time.